Hello everyone. In this video, we will discuss level order traversal and vertical order traversal of the tree. And then we will use these ideas to solve some Leetcode problem to see how they work. Let's look at this binary tree. And for the common traversal strategy, there are three typical types. First is pre-order traversal, and the N represents the current node, and L represents the left subtree, and R represents the right subtree. For example, the first root node is 5, and the left part is 3, and the right subtree is this part. And within and in this right subtree, the first root node is 7, and then the left part is 6, and then the 8. Similarly, for the in order, we traverse the left subtree first, and then the current node, and then the right part. So the left part for the tree is 3, and here the current node is 5, and the right part is this one. And in this part, the current root is 7, and the left part is 6, and the right part is 8. Similarly, for the post order, we first go through the left part and right part, and then current node. For the right subtree, the left part is 6, the right part is 8, and the root is 7. Those are common strategy to traverse the tree. And in this video, we focus on other special cases. First one is called the level order traversal. In this case, we basically use the ideas of breadth first search. So there is a concept of level in the tree. For this one, it is level 0, level 1, level 2. And we go through the nodes in every order step by step. And for the first level, there is only one node 5. And for the level 1, there are two nodes 3 and 7. And for the last level, there are two nodes 6 and 8. So the level order of this tree is 5, 3, 7, and 6, 8. This is one case. And another case is called the vertical order. In this case, we assume there's a grid behind this mesh, behind this tree. And let me use different color. And then we can say that there are different vertical lines here. And for the first vertical line, there is one node, 3. For the second vertical line, there are two nodes, 5 and 6. For this vertical line, there is 7. And for this vertical line, there is 8. So the final results of the vertical traversal for this tree is 3, 5, 6, 5, 6, 7, and 8. Okay, here are some general ideas about the level order traversal and vertical order traversal. Let's use several Leetcode questions to show how they work. Okay, let's look at the question. First one is Leetcode 112, binary tree level order traversal. Give me the root of a binary tree, return the level order traversal of its node value, namely from left to right, level by level. This is an example, and the input is this binary tree, and the output is the output contains several brackets, and in every bracket, it contains nodes in this level. For the first level, there is one node 3. For second level, there are two nodes 9 and 20, and then for next level, it is 15 and 7. in this function, the output is a vector of the vector. So basically, instead of using the brackets, we just need to put different vectors here. So every node will be put, the nodes in every level will be put into a vector. This is inner vector. And for different levels of nodes, we use another vector here. There are two key issues for solving this problem. The first one is to make sure the framework of the recursion. And so the sequence to do the recursive call, basically in this question, we need to visit the current node and then call the left subtree or right subtree. And then another issue is how to visit node, which means what should we do when we visit the current node? And one important thing here is the level information. Since we have two options, either to put current nodes into the existing vector or just, for example, here, when we visit 20, we put this 20 into the existing vector. When we're visiting the 15, and we need to first create a new vector and then insert this 15 into this new vector. So we need to make sure if we need to put the current node into the existing vector or create a new vector. The information of level plays an important role here. Okay, let's look at the code and to work on it from scratch, and we do it together. Basically, we need to first initiate the vector and vector int integer. This is our answer. And here we can use the helper function. And this helper function will help us to traverse the tree and update this answer. And we will return the answer. And we first need the root information of the tree. And another information is important, which is the level information. For current case, the level is 0. Let's add the declaration of this help function, helper. First is this answer information. And then it is a tree node. Then it is the level, or we call it depth. For the start call, the depth is 0. And then in the helper function, we need to first visit the current node and then to do the recursion call. We will consider details in this part later, and we will make sure the general framework of this in this function, because when we visit node and the next step is to do the recursion call and to visit the left node and right node. So we can do things just left and right. Helper, left, root, left. Oh, put answer here. And when we need to increase the depth when we do the recursion call, because they are in next layer, right? Yeah. And then we consider details here. The operation in this function. So first is that we just need to make sure if the current node is a non-pointer. If it is a non-pointer, we just return the results directly. For example, if root equals to non-pointer, we just return. We do nothing here. it directly. And then here is the important part. We need to make sure that we insert the new bracket, which means new vector, or use the current one. So we can make sure we can compute the size of the current results. If the current result is less than depth plus 1, we need to add a new vector. So this is empty vector here. For example, at the start position, the answer is no, there is no vector, so this value is 0. And for the depth value, we start from 1. So 0 is less than 1, and we insert a new empty vector. So in that case, we have this valid value here, depth dot push back. So we can push a current value here. And for the next level, it is level for 9 and 12, it is level equals to 2. But here, our current, the size of the current vector, inserted vector is 1. So we push back another empty vector, and we have this, the expression here will be valid. And yeah, I think that is this code. Let's run the code to see if it works. Oh, train, oh, it should be root here. Oh, yeah. Let's submit it. Yeah, it is accepted as expected. So the idea is simple, and that's the results for the first question. As we discussed just now, one of the key steps for this question is to make sure which level the current node is. We use this answer dot size compared with the depth. And essentially, there are 2 ways to do that. For the recursion method we shown just now, we use visited depths. So this is the answer. This is our answer, and we use it, we compare it with the expected depths. So we can, by this comparison, we can make sure which depth the current node is. And another idea is that we can use the size of Q to do the similar things, and that we will also show the code by this way. And in this way, we do not use the recursion, and we just use a queue to help us to do the level order traversal. Let's remove this part and start from the scratch. We also need an answer here, and instead of then we also need to initiate the vector integer temp. We will put the nodes in the same level into this temp vector, and after completing each level, we will insert this temp vector into this answer. And so we need an answer and root and this temp. So the answer is still this one, root and vector integer temp. Actually, we do not need the helper core. We can just, we don't need the recursion in this code, and we just put it here. Yeah. Similarly for the edge case, if the root is non-pointer, we do nothing, return answer directly. And then, oh, there is a queue here. Queue. The value in this queue is this tree node. Firstly, we initiate the queue and put the root into it. Then we will use the while operation here to check the queue. Make sure it is not empty. If the queue becomes empty, it means that we finish all the works and there is empty nodes in the queue and all nodes have been processed. So queue dot empty is false. And then here, it is important here, we need to check the queue length. This is also the size of the next layer. So for example, for the initiate step, we put the root here and the queue size is 1. It means that we have 1 node in this layer, and then we execute we pop the element from the queue and put the results, put its children into the queue. There is 9 and 20. Then for the next iteration, the queue size is 2. So it means that for next iteration, there are 2 nodes. And size of the next layer, then we process the nodes in this layer. And so here, we first get the level size equals to q dot size. Then we can use another while loop to make sure level size equals to 0. And here we visit the node. After visiting each node, we decrease the level size. How to visit each node? We basically need to pop it out from the queue and get this node value firstly, tree node, current node, and pop it, use front to get this node, and then put it into the temp, this temp vector, because this is a new layer. Temp, this is a current layer, dot push back, put the current node value into this, and then we pop out q dot execute pop. Then we can decrease the level size. So from in this while loop, we process nodes in the same layer, and here we complete the current. Oh, we also need to put the children into the queue. And to this step, we complete the current layer, complete the processing of current layer, and we decrease after we popping out, we decrease the level size and put the children into the queue. Queue dot push. So we can put it here. Things when we pop it out, the things will the memory will be removed. We can put it here. And q dot push current q dot push current left child and q dot push current right child. And if the left child or right child is a non-pointer, it means this current will be the non-pointer. So we should add there might be an issue. We need to make sure it's a valid pointer. So when current left is valid, we push the left. When current right is valid, we push the right. So we only push the valid child. And then when we complete processing the current layer, we can put the current temp vector into the answer. This is a new layer. So this temp contains all the new layer, and we recite this temp since we will process the new layer here. Yeah, and I think that is the whole process for the code. Let's go through it again. If the current node is a non-pointer, we return results directly, then we push the root value, and then we traverse the queue. If it is not empty, we will first compute the level size. If it is greater than 0, we will get the front node and push that node into the temp vector. And if the left is valid, we push the left child. Similarly, push the right child, and then we pop the current node out of the queue and decrease the level size. And then when we finish processing the current layer, we push the results into the answer and recite this and return the answer at last. Oh, there's this thing, typo. Yeah, it is correct as expected. Let's try all the test cases here. And it passed all the test cases. So in this part is really important. We need to have an idea that the current size of the queue is a current level size. And so there are two ways to identify the level of the tree. The first is use the recursion way, and we can record the depth variable. And the second is use the queue size. Okay, let's look at two similar questions. First one is 429, an array tree level order traversal. Giving an array tree, returns the level order traversal of its node's value. An array tree input serialization is represented in their level order traversal. Each group of children is separated by the non-value. We could look at example. This question is similar with this previous one. The only difference is that every parent node contains several children in this example, and the output is also in similar format. The idea is similar with previous one, and we can reuse the code structure in previous question. The only difference is this part. When we do the recursion call and visit the children nodes, we need to go through each node instead of just left child and right child in this example. Another similar one is this question, 107, binary tree level order traversal 2, given the root of a binary tree, returns a bottom-up level order traversal of its node's value from left to right, level by level from leaf to root. So compared with the first question, this one, the difference for this one is that we need to output the value from the bottom to the up. For previous one, we output the results from the up to bottom. The main part, this helper function is same with previous one. The only difference is that after we call this helper function, we use another reverse operation to change the sequence of this output results. So anyway, we can use the ideas of level order to solve those three questions, and they basically use similar ideas. We can either use recursion or use queue-based approach. Let's look at this question, 987, vertical order traversal of binary tree. This is a hard one, but actually it is not that much hard if you understand the details, the ideas behind that. Given the root of a binary tree, calculate the vertical order of traversal of the binary tree. For each node at a position, row or column, its left-right children will be positions row plus 1, column minus 1, and row plus 1, column plus 1, respectively. The root of the tree is at 0, 0. So we assume there is a grid for this tree, and this is the position 0, 0. And if we move from here to there, we add 1 with plus 1 and in the column position and plus 1 in the row position. The vertical order traversal of a binary tree is a list of top to bottom ordering. This is important, top to bottom ordering for each column index, starting from the leftmost column and ending on the rightmost column. There may be multiple nodes in the same row and same column. In such cases, sort these nodes by their values. So there are two important information. One is top to bottom ordering. Another is multiple nodes in the same row and same column. So maybe we will show it later. Maybe we have another child here. And in that way, those two child, this 15 and this, let me use an annotate. Yeah. Assume there is another child here. Maybe it's a 10. In that case, the position of this node will same with, because we add 1 here and add 1 here, so it is the position of it is still to 0. So those two nodes have the same value. So in that case, so we sort those nodes by their values, which means we output 10 first and 15 secondly. Okay, let's look at this example. This is a binary tree, this is input, and this is output. Let's go through the results quickly so to show why it works like this. And the first column here in this tree is the 2. And for this column, there is only one node. It is this one. Similarly, the second column, there is one node and it is 2. And for the third column, the column index equals to 0. And there are 3 nodes, 1, 2, 3. For these 3 nodes, their column index is 0. And according to the description of the question, in this case, we need to first output the nodes from top to down. So the 1 should be at the first position. And if those two nodes are at the same level, we need to output it from smaller one to the larger one. So ascending sequence. And so in that case, we output 5 and 6. So there are two requirements here. If those nodes have the same column value, first is from top to down, and second is from smaller to small value to large value. And for other column index, here when index equals to 1, there is one node, this one, and index equals to 7, only one node here. So that's the results. And another question is that how to store this kind of options, because because intuitively we need to go through the nodes and to store the nodes into a particular data structure, and then we output it to satisfy these requirements. And maybe you could have an idea about a map, and the key value of the map is a column index. For example, when we traverse this tree, we look at the column order, and when it is 0, we put it into the map. When it is a -1, we put it into the map. So by this way, because the key value in the map is ascending sequence, it is sorted. So when we traverse the map, we can get the results from the small index to the large index. But that is a general idea. One important part is what is the value of this this map, and we could look at several options. How about the vector? Can it be a vector? I mean, does the vector satisfy these requirements? Obviously, we go through because here we suppose that the elements is stored in the sequence from the top to bottom. Maybe the vector is okay for this situation, but for another situation, the value should be in ascending sequence if they have the same column value. Maybe in some cases, this value is 6, this value is 5. And if we go through this tree, maybe we'll visit this value firstly, and this value secondly. So the vector does not satisfy our requirements. If we do the ascending sequence, maybe we could try the set. How about the set? And yeah, it is okay for ascending sequence, but in other case, it does not satisfy the requirements from the top to down, because all elements in the side is ascending. In that case, if here the root value is a large one like 10, and the output will be 5, 6, 10. It does not satisfy the requirements. If this is 10, for this column, the output should be 10. And because it is at the first level, and for this level, they are on the same level, and the output is from the smaller to the larger one. It should be 5 and 6. Output for this column should be this one. So the side does not satisfy our requirements. And the actual case is that we still need a map here. And for this map, the K is the raw index, and the value is a multi-site. Why we need a multi-site instead of a site? Because those values might be same, because this can be 6 or this can also be 6. In that case, if we use just a site, we cannot store two nodes or two entry point with the same value. so it does not satisfy the requirements. In that case, like 10, 6, 6, the output should be 10, 6, 6. So we use this row index to distinguish the different row order. We need to make sure the small order, the value with a small row index output first, and then the value with a large row index output before this one. That is why we use another row index here, and the multi-site can make sure that the value in the same level is stored in ascending order, and at the same time, we can also store the nodes with multiple values. So that is a general idea. We need to go through this tree and put every element in this data structure. And then when we get this data structure, we just go through it and to make and print the results out. And that is what we need. Okay, when we have this idea, we can implement it quickly. Okay, let's look at this question. And as we discussed just now, we need to have a map. And the first case is the row column index. And then another map, and the value is another map. And for this another map, the first, the K is the row index, and the multi-site. Multi-set. The element type of the multi-set is also integer. Let's call it my map. And then we use another helper function to go through the tree, traverse the tree, and we need the root value here, and this map structure. And also the index of a row and column. Okay, and we just need to call this helper function and to put elements in this data structure. Root, the value is my map. Second one is my map. At the start position, the row index and the column index is 0. And after that, we go through the map. We will work on this part later, and let's first look at the helper function. And first is the edge case. If the root is a non-pointer, we return it directly, and then we visit the node. If it is a valid node, we visit the node. In this operation, we just put the element into the map. So we put the first index is column. Second index is the row index, and insert. So we get this multi-site here, and then we insert the root value. Yeah, after visit this, we go through the left part and the right part. For the left part, we call the helper root left and my map. For the left node, the column index decrease 1 and the row index increase 1. So it is row plus 1 and the current column decrease 1. And for the right part, both the row index add 1 and column index also add 1. Yeah, that's it for this helper function. Is it node put into in this data structure? Yeah, and when we get these results, we need to go through the map and to put the results into the answer. So we also have this. This is our answer. We defined answer. What is the size of the answer? So the size of the answer, I mean the first dimension of the vector, it should be same with the number of the column. So the number of column is the size of this map. And then we go through the map, use this iterator, first level iterator to go through this part. And then another iterator, let's call it map set. It's .second to go through this inner map, and then another iterator to go through the site value, multi-site value to go through, yeah, this .second. Here we can put the value into this answer. Yeah, we need also need dot push back set. We also need an index here, int equals to 0, and for each column we need to add the index and return the results here. Let's go through the whole program to check everything is good. We initiate a map here, and then we call this helper function to go through the tree and put elements into the map. And then we go through this map. In this helper function, we first check the root, and then when we visit every element, we put it into this map. First is a column, and second dimension is row, and we insert the root value. Then we go through that. Oh, this should be right. We check the left part, and for left part, the row index increase 1 and the column index decrease 1. For the right part, the row index increase 1 and column index also increase 1. And then when we go through this map, for the first layer, we use the iterator, and then the second layer, and then the inner layer. For the inner layer, we just put elements into this, into the particular position, because the sequence of the output is according to this data structure. The output sequence of this, the value in the multi-site is as expected in this order. I mean, it satisfies the requirements, so we just put the value here directly. And yeah, let's look at how it works. If it works, oh, it should be I here. Yeah, the results looks good. Result looks good. And yeah, it passed all the tests. Thanks. I think that's all for this video. And we go through several questions to understand the ideas of the level order traversal and vertical order traversal, and use several questions to show how this idea work in real problem. Yeah. Thanks for watching for this video, and see you next time.